Hello everyone, welcome to the one shot for P Block Group 14. In this series, we are covering P Block from scratch for JEE Mains or NEET level, and we are covering the entire NCERT portion which is relevant for your syllabus. And so, without further ado, let's begin. Today we are going to learn about the Group 14 elements of the periodic table. What are the Group 14 elements? They are carbon, silicon, germanium, tin, and lead. You have to remember these, of course. So let's start with the basic facts which you have to remember. Like they should be written on your heart. Make sure the examiner can't see your heart, otherwise they'll frame you for cheating. But yeah. So carbon is 17th most common element. Like it is found almost everywhere, like in the earth's crust. In fact, 18% of our bodies is made of carbon containing compounds. In fact, the element of carbon is so versatile that there's an entire branch of chemistry dedicated to it, which you must be familiar with: organic chemistry. I know it has caused you a lot of problems, and maybe one day I'll start teaching organic too, who knows. So carbon is the 17th most common element in the earth, and it is found in common forms such as coal, graphite, or diamond. If you didn't know, diamond is a form of carbon only, like it's pure carbon, and it constitutes about 0.03% of the air in the form of CO2. I want to remember that. Now, what are the isotopes of carbon? Carbon has three isotopes. First of all, there's the most common one, which is 12 carbon. There's 13 carbon, and there's 14 carbon. This one is the most common one. This one is still fairly common, but the last one, it is radioactive, and it is radioactive with an insane half-life of 5770 years, and due to its long half-life, it is used in fields like radiocarbon dating. Now, what does radiocarbon dating mean? It does not mean dating a carbon which is radioactive. Radiocarbon dating means using this, like basically using the remains, you know, the half-life. So basically you know the rate constant. You must have read in chemical kinetics, and using that rate constant you can estimate the concentration of basically numbers of nucleons of the 14C which have decayed over time, and if its concentration is X right now in 2026, what was its concentration back like many years ago? I mean, let's say minus 2026, like basically 2026 BC. What was its concentration back then? So you have its rate constant, you have its half-life. So using that you can find, I forgot the equation, but original upon new, its natural log is equal to rate constant into time, and the rate constant here will be the natural log of 2 divided by 5770 years. We are not going into calculations, you know what I'm saying, right? This is not mentioned in the NCERT, of course. It just mentions that it is used for radiocarbon dating. I just explained you what radiocarbon dating is and how it's done. Now let's learn about silicon. First of all, silicon is atomic number 14, and it is the second most common element. Around 27% of crust exists in the form of silicon compounds like silicates and etc. And it is the second most common element only after oxygen. That's all the NCERT mentions for some reason. Now let's talk about germanium. What is germanium? Germanium is present in the earth crust in very small amount. Like NCERT mentions this word traces. Traces, you know, like these are traces. Like Very small separated segments of germanium are found all throughout the earth, and hence it is not that common. Now let's talk about tin. You must have heard of tin cans, tin foil. Tin's atomic symbol does not represent its name, it's just SN. Tin is found in its ore. What is the name of the ore? It is cassiterite. That is a very fancy name, and honestly, I love this name. Like, it just hits a nerve in my brain or something. I just love how it's spelled. And its formula is rather simple compared to the ones we studied in last class, which are boron and aluminum ores. Its formula is just SnO2. Basically, it's just an oxide of tin, which we can use to obtain tin in raw form. Now there's lead. Lead is obtained in the same way from its ore, and its ore is called galena. Galena. I love this name as well. It's fancy. Galena. Like, it's fun to say. But yeah. Here it is. Formula is PBS. Now I want you to note something interesting. You see how here the oxidation state of tin is 4, while here the oxidation state of lead is 2. You say, like, this kind of illustrates the inert pair effect, because as you move down the periodic table from Sn to Pb, the plus 2 oxidation state got more stable, and hence lead naturally occurs as a compound in which it has the second oxidation state. Isn't that cool? Pretty cool, I guess. Wait, why have I written pH? It's Pb. Don't think any other meanings for pH. Yeah. Now, I want to tell you about one element, which is Fl, flerovium. The NCERT mentions some minute info about this, and just like nihonium, its chemistry has not been established yet. Its electron configuration is basically that of radon plus 14 F electrons, 10 D electrons, 7 S2, and 7 P2. That's it. That is the electronic configuration of flerovium. You don't have to remember this. Just the NCERT mentions it. I don't think they would ask you that. Its atomic number is 114, and its atomic mass is 289. And yeah, that's it. Its chemistry is not established. It is radioactive. Like, basically everything above bismuth is more or less radioactive, and we haven't been able to study them to that substantial amount of knowledge we have above other elements which are lower than bismuth. But yeah, that's about it. Now comes the important portion from which you will notice the most questions in your JEE mains or NEET examinations, which are the trends. Now, what are the trends of group 14? The trends of group 14 are there is a constant increase in radius from top to bottom. Why is that increase constant? Because of course the value of n, principal quantum number, increases as we move top to bottom, and hence the number of shells increases. And since the number of shells increases, the radius does as well. Now, its ionization enthalpy follows a weird pattern. It drops from carbon to, wait, I'll use blue color to write this, so if you download the PDF it will be clearer to you. Carbon is greater than silicon here. Like, of course it is a smaller element, so it will have more pulling power from the nucleus, which we call nuclear charge, and it will be harder to abstract an electron from its outermost shell. And for the same reasons, silicon is greater than germanium, and germanium is greater than tin. But thanks to lanthanide contractions, the exception here lies in the fact that lead is slightly greater than tin. Lead is still smaller than all of these, but it's like For tin it is 708, and for lead it is 750. It is a very minute difference, but still a difference is a difference, and it's worth noting that the ionization enthalpy increases from Sn to Pv but decreases from carbon to tin. And of course, one more point I want to say here, the ionization enthalpy of group 14 elements is greater than corresponding group 13 elements. Why is that? Because see, for group 13 the configuration is like whatever into ns2 np1, and for group 14 element corresponding it is whatever into ns2 dot np2. Now here you can see that if I remove an electron from the group 13 element, it loses its p electron, and this shell just vanishes, and we are left with something which has a positive charge and a fully filled s orbital. But here, if we take away that one electron from the group 14 element, we are left with np1 with a positive charge. So this does not give us anything significant, only the two fully filled s orbitals and one estranged electron, which is not appreciated by the dynamics of our universe, and hence the ionization enthalpy of the second is greater than first. I hope you understand why the ionization enthalpy is greater. It's because to reach something more stable, you have to provide lesser energy. Like there will be a bit of spontaneity in removing the electron, because the system will also favor that here. But here it will not favor that, because what benefit does the system gain from having a stranger electron just roaming around in its atom space? I don't think anybody would appreciate that. Would you appreciate it if an electron just kept revolving around you and irritating you for no reason? Exactly. Now let's talk about electronegativity. The electronegativity, I guess you have to remember the values. There is a very weird pattern here, that it is 2.5 for carbon, but of course it depends on the type of bond. In higher bonds like C triple bond C, this can go greater than 3, but in pure elemental state the electronegativity of carbon is 2.5. Now, an interesting thing to note is that for silicon, germanium, and also tin, all of them have the same electronegativity, which is 1.8, according to the Pauling scale given in NCERT. And lastly, the lead has a slightly higher electronegativity than this trio, which is 1.9. So if I had to describe this trend, it goes somewhat like this. Carbon is up here, then rest of the three are on the same level, and lead is just slightly higher at the end. So maybe this graph can help you remember the thing better. Let's call this a boat graph. Yeah. So that was it about the electronegativity. Now I will teach you about allotropes later, but for now I want you to know that carbon exists in three forms, two of which are diamond and graphite. Now, why am I mentioning this point right now if I'm not going to teach it? It's because we need to talk about the density. Let's move this point here. Oh, it's big. Yeah, so let's remove this. It was just for explanation. So let's talk about density. If we talk about how we normally obtain carbon, which is graphite, like graphite is in your pencils, the lead of your pencil is made with graphite, and it is also used in a lot of other industrial mechanical stuff also. If we take Siga of graphite, then it's the density of group 14 elements just increases top to bottom. What does this mean? That the density of silicon is greater than graphite carbon, silicon is lesser than germanium, which is lesser than tin, which is lesser than lead. But if we talk about, say, C diamond, then what happens is that the density of C diamond is greater than that of silicon. That's it. And of course, it is also greater than that of graphite. But in comparison to the rest of the elements, they are still greater than C diamond. So the overall order becomes C graphite is the least, then silicon, then C diamond, then germanium, then tin, and then lead. This is the order of density of group 14 elements. And this is just written in NCERT. The exact explanation behind this is deleted from syllabus, but I'll just tell you. The tin we are considering here is the beta form of tin. Tin exists in two forms, which are alpha and beta. It has something to do with how their atoms are arranged in the lattice, and I won't dive into that because I don't know solid state yet. Did you forget I am a student just like you? But yeah, that's it. I am telling this because what if they ask us in mains that what form of tin is following this order of density? So if they ask you, you have to take beta. Now we are done with the trends of group 14. How much time has it left? 16 minutes. Now let's talk about the physical properties. What are the physical properties of group 14 elements? This is a very small section, it will be finished in this page only. Physical properties is basically carbon and silicon are non-metals and form acidic oxides. Germanium is a metalloid, which means it follows the properties of both metals and non-metals. And tin and lead lie on the metallic side of the spectrum, and they form basic oxides, more or less. Well, not really. I'll show you what exactly happens. But yeah. And one last thing, they asked a direct question in 2025 this year. Their melting points and boiling points are greater than that of the comparative corresponding group 13 elements. Yeah, that's it. Now, let's talk about the chemical properties of group 14 elements. What chemical properties do these guys show? So obviously, in most of the cases, plus 4 oxidation state they show. They can also show plus 2 oxidation state, and carbon can show negative oxidation states as well. For example, in carbenes like Al3C4, not given in NCERT, I am adding it for extra understanding. And the plus 4 state tends to form covalent compounds. Not all its compounds are covalent, but the plus 4 state, as you know, as per Fajan's rules, it is a very good puller of the electron cloud. Like this is cation, this is anion, this is anion's electron cloud. So the cation is really good at pulling it towards itself, which increases the covalent character. And the greater the charge on the cation, this phenomenon is more pronounced. So that is what Fajan's rule says. And since the plus 4 state is a really good oxidation state for such covalency, so most plus 4 state of oxidation state compounds are covalent. Now this has exceptions which we will study in the future. Now, one very basic thing which I told you in the last lecture as well. The stability of the plus 2 oxidation state increases as we go from top to bottom as per the inert pair effect. What does this mean? It means that lead 2 gets more stable than lead 4, and overall the stability of the second oxidation state with respect to the fourth oxidation state, this tendency basically, it increases top to bottom. Now, what do the individual elements show as oxidation states? Carbon, silicon mainly show plus 4, while carbon can show negative ones. And germanium shows plus 4, but in very rare cases it can show plus 2. But this is only the beginning. This is only the beginning of this stability of the plus 2 oxidation state. Its villain arc has just begun. Now if we talk about tin, tin in its second oxidation state is reducing. What does this mean? What does it mean for this oxidation state of tin to be reducing? Well, if it is reducing, that means it has a tendency to attain the fourth oxidation state, because if it's reducing something, it wants to get oxidized itself, and oxidizing means loss of electrons, which will increase its oxidation state. So here, as we see, while this fourth oxidation state is still more stable than the second oxidation state, we can say that this has started to exist as a separate entity. And finally, when we talk about lead, lead in the fourth oxidation state is highly oxidizing. What does this imply? If it is a very good oxidizing agent in the fourth oxidation state, that means it wants to lose electrons itself. No, sorry, it means to gain electrons and get reduced itself. If this is a good oxidizing agent, then this reaction where it gets changed from the fourth oxidation state to the second oxidation state, this will be a highly spontaneous reaction, and this means that the stability lies on the right hand side. The product is more stable because we can judge by looking at the spontaneity of this reaction. And this is where the villain arc of the plus 2 oxidation state has been completed, and Pb twice is much more stable. I think that is enough muches. Much more stable than the fourth oxidation state of lead. Now, one more point the NCERT mentions, but I don't find it really interesting. But just remember it. Compounds like SiF62 minus or GeCl62 minus, they can exist where the covalency of the central atom is 6 and they hold a plus 4 oxidation charge, oxidation state. But these compounds are out of reach of our dear carbon. Why so? Because carbon cannot expand its octet thanks to having no d orbital. Now let's talk about the oxides. Oxides are very easy to remember. Let me know if you want me to make a separate video for oxides of all the relevant elements of your syllabus. But for now, let's talk about group 14 only. If you say there's CO2 or there's SiO2, you know these are non-metals. So these oxides are acidic. As I explained in the last lecture, how if you not dissociate, but add CO2 to water, it becomes into HCO3, H2CO3, and this breaks down to give H plus and HCO3 minus. So, judging by how they behave in an aqueous solution, we can call an oxide acidic or basic. So, if you put either of these in an aqueous medium, they will become into a compound which can dissociate into a base and an H plus. And this is how they are termed as acidic or basic. Understood? Now, the oxide of germanium is acidic as well. While the lesser known SiO only exists at high temperatures. The NCERT does not mention whether this is acidic or basic, so they won't ask you that. Just remember that it exists only at high temperature. Now, any oxide of tin or lead, be it SNO, SNO twice, PbO, or PbO twice, these are always amphoteric. not basic. I know they have high metallic character, but the NCERT calls them amphoteric, so you have to call them amphoteric. If your father's name is Ramesh Kumar and NCERT tells you that no, it is Rajesh Kumar, you have to come to terms with the fact that your father's name is Rajesh Kumar. Forget who Ramesh is. Your father's name is Rajesh. This was no offense, just to understand the importance of what NCERT says, okay? The NCERT provides a lot of misinformation, but you have to remember them like they're the holy grail of inorganic chemistry. And what can you do about it? Nothing. Now let's talk about the chemical reactivity. Like how do they react with stuff like water, air, etc. Let's just talk about that. Let's go. Now with water, you will be happy to know, but also you may be shocked. With water, out of all the five elements, only 10 reacts, like only SN, and the reaction is SN plus H2O. Balance, do it yourself. SN plus H2O gives SNO2 plus 2H2. ये तुम भी याद रखोगे. SN plus 2H2O gives SNO plus 2H2. That's it. Only tin reacts with water, and none of the other elements like carbon, silicon, germanium, lead, they don't react with water. Like it is speculated that lead might react, but if it reacts, it forms a protective layer which prevents it from further reaction, and basically it self sabotages its own reaction. How pathetic. Now let's talk about halides. Halides, of course, exist in two forms like MX2 or MX4. Now, the rules of the inert pair effect apply here. If they ask you whether this halide is more stable or this halide is more stable, just look at what kind of element the M is, and therefore you can form your answer based on the inert pair effect that I have explained over here. The NCERT explains a detailed paragraph. Like, in fact, let me show you. If you go here, if you go here, P-Log 1314, the NCERT has this entire yapping just telling you that this is covalent, that is covalent, may. Just shut up and apply the inert pair effect. It's just yapping. Now I will mention the important points which the NCERT states separately, which is that the fluoride of tin, the fluoride of lead, and the iodide of lead, these show exceptions. First of all, these two, they are ionic. Like I told you here before, that +4 oxidation state tries to make covalent compounds, but these two are rule breakers. They tend to be ionic. And this is because the fluorine anion, it is incredibly small. Like it is small, very small. And because of its smallness, it has a very poor electron cloud. And no matter how good of a cation you bring near it, like say you have carbon 69 plus, it won't be able to pull shit from here because there is no shit to be pulled. And which is why Fajant's rules just stop working. I mean, they don't stop working, but they cannot find a loophole here, and hence these salts are ionic. And the special part about PbI4 is that it does not exist. Like this compound is too bulky. I wouldn't say bulky, but it's basically the PbI bond. It's not energetically favorable to form this bond, like doing all the unpairing of the electrons, hybridization, way. It's just not favorable. It does not deserve to be formed. If you want to read the exact NCERT line on this, you can just look here. You can see it says that PBI bond initially formed during the reaction does not release enough energy to unpair 6s2 electrons and excite one of them to higher orbital. What is this yapping? Just say, it does not exist. It is not energetically favorable. You don't have to tell that much. Excuse my weird behavior today. My cold has gotten worse and my neck hurts like shit. But yeah. Now, let's learn about hydrolysis of these halides. How do I hydrolyze these halides? Now, except for CCl4, all the halides show hydrolysis. How do they show hydrolysis? Like say, for example, I have SiCl4. This is a halide of a group 14 element, as you can tell. If you are not able to tell this is halide of a group 14 element, the problem is either with you or either with me. So SiCl4, if you add water to it, and specifically if you add 4 moles of water to it, it forms SiOH whole 4, which is silicic acid. Remember the name, it may be asked. It forms silicic acid, and basically what has happened is the water has acted in this reaction and it has sent its hydroxide ions to replace the chloride ion, and that is how this compound has been formed. This is how hydrolysis of halides take place. Now, let's talk about catenation. What is catenation? Catenation, as you know, it's basically the tendency of an element to form bonds with itself, like carbon-carbon. Basically, incest. No, I mean, basically it is tendency to form bonds with other atoms of its same family. So, if it is single bond, say, wow, I like this person. Let's make another bond. Oh, teri, I like this person again. Let's make another bond. Like basically, it is loyal, right? That is the best way to explain it to you guys. It is way too much loyal, so it just makes bonds with itself. That sounds bad. Okay, leaving this topic, just remember this. The tendency of catenation. What has happened to my speech? The tendency of catenation. It is carbon has a much greater catenation tendency as compared to silicon, which has greater tendency than germanium, which is comparable to that of tin. These two have almost the same catenation tendency. And lead. You can call this the Sasuke Uchiha of group 14. It does not like its family. And it just does not form bonds with itself. Yeah, it has zero catenation tendency. Well, that's it. I have covered all the major points. There's one more last thing to cover, which is allotropes of carbon. What is an allotrope, you may ask? Allotrope is basically if one element can exist in multiple crystal lattices. For example, say one element is existing in this cube like lattice, but it is also existing in this hexagonal lattice. I don't know what this is, but it is the arrangement of its particles in its solid state. That is basically what allotrope is, and these two are called allotropes of the same element. So we only have to study the allotropes of carbon. So first let's quickly study about diamond. Diamond is basically a connected chain of carbon atoms like this. It is basically what you call a tetrahedral structure. Like these are all connected. In fact, the NCERT shows you a better diagram than me. Don't rely on my drawing. You can see basically here, as you can see, this one carbon, oh, the brush size, the one carbon is attached to like 4 carbons like this, and these are attached in the similar fashion to 4 other carbons. Like this one isn't shown attached to anybody because it's the photo is taken from the front, but here you can see this is attached to 4 carbon, then this is attached to, yeah, they are terrible at making diagrams, but better than me, of course. You understand how this entire thing looks, right? And basically you have to remember that this bond is 154 picometers. It is very difficult to break these bonds. Like, if we talk about these bonds, they are very well arranged together, and this is a very, strong structure. And in fact, this is the same structure which is followed by, say, SiC or SiO2. And this structure in itself is very difficult to break apart, which is why diamond is one of the hardest substances on earth. Okay, that's it. Let's learn about graphite. In fact, I am terrible at making diagrams, so I'll just teach using the NCERT only. The graphite has layered structure. They're held by van der Waals forces. Like, it's like this. Imagine there's two plates on top of each other, like this plate and that plate, and these can slip between each other, like this plate, this plate. Basically, this can happen. Yeah. Of course, this sound does not come. That was for dramatic effect, but you know what I mean. And this bond here, it is 141.5 picometers. Like, the basically it's the size of this plate. Like, this is multiple plates together, which do over each other, and the size of one plate is given as 141.5 picometers. And the average distance between the plates of plates is given as 340 picometers. It is pretty huge difference. And basically in mains they can ask that, is the carbon carbon single bond greater in diamond or greater in graphite? So there you have to remember it's greater in diamond, but the distance between the plates is almost 3 times, no, it's close to 2 times the diamond distance. Now, yeah, same point of 141.5. Each carbon atom here has sp2 hybridization, because you see this is not exactly counted as a bond. This is not exactly a bond. It's just it's a situationship. It's not a relationship. It's just there without any purpose. It just binds the sheets together, and each carbon you can see it's bonded with only 3 more carbons, like proper bonds. So this is just a sp2 hybridization, and hence along this entire sheet there is an aromatic character. Like, this is not shown, but there is an aromatic character, and this causes there to be a ring current. Aromaticity causes ring current, and basically the electrons are free to move way. They're free to move wherever they want all throughout the sheet, and which is why graphite conducts electricity along the sheet. Like, this electricity can be conducted well on top of the sheet, bottom of the sheet, because of this factor only, aromaticity. And of course, as I told you, the sheets can slip over each other, so it is very soft and slippery. Graphite is used as a dry lubricant. Like, it is just like, I would tell you, search it on YouTube. It's funny how, despite being a solid, how viscous, maybe you can say, how viscous graphite is. Like, it just flows on top of one another, and it's really fun to watch. Go check it out. And finally, let's come to fullerenes. Fullerenes are made by heating of graphite in electric arc in presence of inert gases. I am highlighting this because mains asked a question on it, and this gives rise to very a huge amount of fullerenes, especially C60. And C60 has a shape like soccer ball, and it's called Buckminster funnel. Now, mains has asked questions on this like 226 times. This was an exaggeration, but this means I'm telling it's important. It has 26 membered rings. 20 and 6 is different. Like, this is a 6-membered ring, and Buckminster fullerene has 20 of them. And this is a 5-membered ring. Buckminster fullerene has 12 of them. 12 5-membered rings. It looks like a standard soccer ball. Like, if you see a soccer ball, it also follows the same ring pattern. And that's kind of like it makes me wonder, there is another parallel between the atomic scale of things and the real life scale of things, and somehow we figured out that the most optimal way to make a sphere using polygons was to use 20 hexagons and 12 pentagons. It's spectacular to think of, but coming back to the topic, all carbon atoms are equivalent, like identical, and they undergo sp2 hybridization. Each carbon forms 3 sigma bonds with 3 other carbons, and the remaining one is delocalized, which give aromatic character to the molecule. Now, of course, it has 60 vertices since there are 60 carbons, and each one is occupied by one carbon atom, and it contains both single and double bonds with distances of 143.5 and 138.3 picometers respectively. And these are also called buckyballs. And last thing I wanted to know, that graphite is thermodynamically the most stable allotrope of carbon, and in thermodynamic terms, its standard enthalpy of formation is taken as 0. You don't need to remember this, but just know that for diamond and fullerene, these values are non-zero. Well, sorry for switching to the NCERT at the end, but there was no way I could draw these diagrams as perfectly, so I just stole it from the NCERT. And the rest of the points I have explained in this lecture. And yeah, that's it. If you want the notes, do let me know. Here I have group 13 as well. And basically that's everything you need to know about the group 14th of periodic table. Thank you.